You ever wonder how your voice, with all its personality and emotion, gets squeezed into a tiny little data stream for a phone call? Well, today we're diving into the wild science of speech compression and a brand new AI that's trying to shrink the human voice down to its absolute bare bones essence.
So let's start with a number that sounds like it's pulled straight from a sci-fi movie, 100 bits per second. Now, it might not look like much, but for researchers in this field, this is the holy grail. It's the theoretical finish line in a race that's been going on for decades.
So, what's the big deal with 100 bits per second? Well, it's the estimated absolute rock bottom data rate you'd need to perfectly transmit English speech. And I'm not just talking about the words, but the speaker's identity, their tone, every little inflection. It's the floor, and we are not even close to it yet. To really put that 100 BPS goal in perspective, just look at this. Raw, uncompressed audio, it's a total data hog. We're talking almost 1,000,000 bits per second. But with some clever compression, we can already get intelligible speech down around 450 BPS. I mean, that's a massive diet. And it's what makes things like digital amateur radio or mobile phones in really low bandwidth areas even possible. But how do we get even smaller? Well, the answer might be in how we actually speak. Okay, let's get into this, because your own voice is this surprisingly simple, really elegant system. To figure out how to compress speech, we first got to understand the basic recipe for how we make it in the first place. It really just boils down to 3 key ingredients. First, for sounds like vowels, think ah or ooh. Our vocal cords create this periodic pulse, basically a buzz. Second, for consonants like s or sh, we generate something that's more like random noise, a hiss or a pop. And third, and this is the magic part, our mouth, our throat, and our nasal passages, they act as a physical filter, shaping that raw buzz or noise into the sounds we all recognize. So, how does this all connect to AI? Well, the researchers behind this new model decided, hey, instead of just crunching audio data, why don't we build an AI that directly copies the biological process we just talked about? They basically taught a machine our own recipe for speech. And the parallel here is honestly remarkably direct. The AI has a buzzer layer to create those voiced sounds, a noise layer for the unvoiced sounds, and then a formant mask that acts like a digital mouth, shaping those raw sounds into actual speech. It's a truly bio-inspired approach to a very digital problem. Now, the type of AI they're using here is called an autoencoder. You can kind of think of it like an expert forger and a super efficient summarizer, all rolled into one. Its first job is to look at a piece of speech and encode it, squishing it down to its most essential information. Then its second job is to take that tiny little summary and decode it, rebuilding the original sound as perfectly as possible. So the theory is pretty elegant, right? Build an AI that works just like a human voice. But the real question is, does it actually work? How does this new model perform when you put it head-to-head against other state-of-the-art compression methods? So, yeah, how does it stack up against the competition? Let's take a look at the data. And the results are really, really interesting. So in this test, they put their new model up against several of the big guns, the open source Codec 2, Meta's Encodec, and the highly specialized LPCnet. They measured them on a few key things. Eastoy, which is mostly about intelligibility. Can you understand the words? Then PESC, which measures the overall perceptual quality, and WarpQ, which kind of predicts how a human would rate it. And as you can see, their model, this work, is extremely competitive. In fact, it actually scores the highest on PESC, that perceptual quality, and it's neck and neck with LPCnet on that WarpQ score. This proves that this whole bio-inspired approach, it can absolutely hold its own against the very best. But, numbers only tell part of the story. To really see the differences, we can actually look at the sound itself using something called a spectrogram. It's basically a visual map of the audio. And one of the best things about this research paper is how honest the authors are. They point out in their own analysis that their model's spectrograms look a little blurry. And this is probably a direct result of their design. That formant mask we talked about is created at a lower resolution and then scaled up, which can smooth out some of the sharper details. It's a classic trade-off, really, efficiency versus precision. They also give props to a competitor, LPCnet, noting that it produces spectrograms that look closest to the original uncompressed audio. It's a great reminder that even though their new model is super powerful, there are different ways to get to high quality, and a super optimized model like LPCnet still really shines when it comes to creating a visually similar output. So where does all this leave us? We've got this new, really competitive model that's built on a simple, elegant idea. It gets us one step closer, for sure. But that 100 bits per second dream, it still feels a long way off. So what's the next step? Okay, before we get to the final thought, let's just do a quick recap. The human voice has a simple 3-part recipe: buzz, noise, filter. We can now build AI to copy that recipe, and this new approach is already competitive with the best models out there. And finally, that incredible shrinking voice still has some more shrinking to do to hit that theoretical limit. And that brings us to the final, really provocative idea from the paper. To make that next great leap in compression, to get really close to that 100 bips limit, maybe it's not enough for an AI to just mimic the sounds we make. Maybe, just maybe, it'll need to understand the meaning behind them. A fascinating thought to end on. Thanks for tuning in.